Hello, everyone, and welcome to today's webinar. My name is Nico Genis, and I'm a simulation applications engineer here at Simcenter. Who we are as Simcenter is we are a value-added reseller of Siemens, focusing on the products that were acquired from Altair. And today's focus will specifically be on Simcenter EDEM. And with that, I would like to welcome Senthil and Prasad from the Siemens team, and also give Senthil the opportunity to do a quick introduction of them as well. Thank you, Senthil.
Thank you, Nico. Hello, everyone. Greetings. I'm just going to share my screen.
There we go.
Okay, great. Thank you very much. Again, thank you, everyone, for attending the session today. My name is Senthil, but I would like to provide a few introduction slides before I hand it back to Nico, just to introduce ourselves as who we are and stuff. But I think to start with, I'm part of Siemens AG, but within that, Siemens is a big conglomerate. We are part of the digital industries division within Siemens, and within digital industries, we have the software domains, which is the digital industries software division, and that's where I'm from. But even within that, digital industry software is a market leader in industrial software. But our business unit is specifically focusing on the simulation aspects of it, and as you can see here, it's focusing on simulation. It's focusing on customers, how we can actually help the customers in optimizing the process and equipment using virtual modeling techniques. Again, different techniques, different solutions. Siemens offers the industry's most comprehensive physics-based digital twin that extends over the life cycle of a product or a process across industries and across domains, including mechanical, electrical, electronics, fluids and thermal, semiconductors, manufacturing, operations, etc. So the comprehensive digital twin is generative and adaptive, providing all the data that is needed, all the data that is being handled as well. So everything from end-to-end systems we are actually able to provide on this. So with that introduction, I'd just like to introduce Andrew, Dr. Andrew Greimer, who's a seasoned engineer, thought leader, and Chief Operating Officer of Bulk Materials Engineering Australia, a distinguished consultancy affiliated with the University of Wollongong. With a rich background in research and commercial ventures, Andrew has left an incredible mark on diverse industries. His expertise encompasses simulation, troubleshooting, audits, and the design of bulk handling plants. Andrew's exceptional portfolio, includes projects ranging from intricate problem solving in bulk materials handling to pioneering advancements in technologies like dust suppression and DEM material calibration. So with a robust history of optimizing materials, Andrew has propelled the industry forward. He's truly a thought leader, and and you're going to hear more from him over the course of this session here. Myself, my name is Senthil Arumugam. I'm based out of our UK office in Scotland, in Edinburgh. I'm leading the global business for all our particle solutions from Siemens. And along with me, I have my colleague Prasad Avilala, who's an expert DEM and FEM engineer. So he's a senior customer support engineer, and we both will be happy to take any questions that you may have. So please use the chat window to ask your questions as the session is ongoing. We'll be happy to answer all your questions. I think just to set the stage, this exclusive online workshop will delve deep into the use of DEM, using EDEM technology, Simcenter EDEM technology, for advanced design and simulation techniques for optimizing transfer chute performance. At the end of this session, hopefully you will be able to learn to apply the results of material flow property tests to improve your operations and design efficiency, deepen your understanding of key concepts in transfer chute design to enhance your professional skills, of course, allow you to learn effective methods for diagnosing problems, optimizing designs, and implementing best practices in your designs itself. So again, increasing your knowledge of real-world material behaviors and the phenomena that you're observing during the operations, etc. So all of those things you will be able to potentially learn over the course of this session. I think without taking much of time, I just wanted to talk about the challenges. Why are we here as well? The challenges is particularly involving the bulk materials. As you all know, you're coming from the industry, so the challenges involving the material, the different materials that changes over a period of time, causing a lot of problems in the handling side of things, material handling side of things. Just an example, if you take free-flowing sand, it could be dry and very easy to handle one day, but after an overnight rain shower, the same free-flowing sand can become cohesive, extremely difficult to handle. And when you're designing a material handling equipment, keeping in mind with one type of material, and after these environmental condition changes, the same material behaves completely different. And that's where the challenge comes in. And that's where a lot of our customers, a lot of the engineers who are involved are trying to address those kind of ever-changing material behaviors and the challenges associated with that as well. So with that, I would like to hand it back to Nico and take it from there. Thank you.
Perfect. Thanks, Sintu, for the introduction. We will now move over to the webinar. Just two arrangements before we do so. If at any stage you have questions, you can submit it through the Q&A. We will then either attend to them during the webinar or answer them in the live Q&A at the end. And then if you need to jump off at any stage during the webinar, don't worry, a recording will be sent out afterwards to all that registered. Then without further ado, you can enjoy the webinar.
Hello, and welcome to this webinar on advanced design and simulation modeling techniques for optimizing transfer chute performance. I'm Andrew Grimer, and I will be the host of this webinar today. For those that are not familiar with me, I'm an application engineer for Altair, specializing in EDEM simulation tools, and also the Chief Operating Officer for Bulk Materials Engineering Australia, which is a licensed consultancy group that operates out of the University of Wollongong. So I've got a lot of experience with bulk materials testing and design and optimization of bulk material equipment, in particular conveyor transfer chutes. So in today's webinar, I'd like to share some of my knowledge and know-how when it comes to transfer chute design, but also show how we can use simulation tools and traditional design methods to optimize our transfer chutes for utmost performance and reliability. So just a quick overview of the agenda for this webinar. So in the first half of this webinar, I will be providing an overview of the theory and analytical models that are available, which can be used to design our transfer chutes and evaluate our material velocity and behavior. And then we'll have a short, just little session break. And in the second half of this webinar, I'll introduce and we'll talk a bit more detail about discrete element modeling, which is a simulation tool for modeling granular and bulk materials. And then we'll introduce the EDEM simulation technology and also talk about some of the co-simulation capabilities for design and validation purposes. And then we'll also talk about an important topic of material characterization and testing, because it's quite important to understand the bulk material that you need to design your conveyor transfer chutes for. And we also use this material testing for DEM calibration purposes, basically to calibrate our mathematical models and parameters for discrete element modeling. And then I would also like to support and show some examples and case studies of various transfer chutes and bulk material handling equipment that I've worked on over the years, and also provide a demonstration of the Altair EDEM software for chute design. And then at the end, we'll have a Q&A question. So if you do have any questions, you're more than welcome to note them down, and I can address them, or we can address them in the Q&A session. But if you also do have any other questions, you are more than welcome to email me with the email shown on the screen. So conveyor transfers are not new. They've been around for a long time, since the inception of conveyor belt systems. They are in all sorts of shapes and sizes, but essentially are used for conveying product from one conveyor belt or one bulk material handling equipment to another bulk material handling equipment. But often, when they're not well designed, they can be very costly in terms of operating and maintenance costs. So typically, conveyor transfer stations can account for, somewhere in the vicinity of 70 to 80% of wear-related issues on a conveying system. So typically, you find that, a lot of the time, wear liners in your chutes tend to wear out quicker than your conveyor belts themselves in terms of the top covers and bottom covers. And then typically, about 60% of the total conveying maintenance time in the iron ore and coal operation systems is spent on conveyor transfer chutes. Okay, so you can see there they are quite important bits of infrastructure in a bulk material handling plant. So some of the common failure mechanisms include wear of your liners or detachment of your liners within your chutes, blockages, especially when handling wet and sticky ores, or even sometimes when you get very large surges, you can block your chutes. You can also have high dust emissions, which can cause visible health risks. But another sort of common problem and hassle within the industry is material spillage that requires a lot of material cleanup and housekeeping to keep the the spillage levels at a manageable point. So we can often redesign and optimize our transfer chutes to minimize these common failures. So in a typical sort of plant, in terms of what's the sort of cost when some of these transfer points fail or there is downtime associated, it can depend on the commodity price and the sort of throughput of that operation. But in some circumstances, you could be seeing costs of somewhere between 180,000 and 250,000 per hour US dollars for any sort of downtime. And typically, sometimes the downtime from chutes can represent about 10 to 20% of the total downtime within the mining operation. So therefore, it is quite important to utilize advancements in simulation-based design to model and optimize our bulk material handling equipment to minimize the downtime. Okay, so this is what we'll be talking about in today's webinar, about how we go around about designing these chutes and minimizing any downtime using the latest tools and technologies available. So, transfer chutes can be small and they can be very large in some operations, handling somewhere from, a couple hundred tons per hour to, somewhere in the vicinity of, 20 to 30,000 tons per hour. So there are varying complexities with your chutes, and the main idea with a chute is to redirect product to load conveyor belts or bulk material equipment, and also to unload the bulk material from that equipment as well. Okay, so typical sort of plant layout with multiple conveyors, it's quite easy to have a high number of conveyor transfer points. Obviously, a lot of the time when we do plant designs, we want to try to minimize transfer points because, as we talked about before, is that they're typically a common cause of high maintenance. So less transfer points you have, the less maintenance costs and downtime associated with that. So often the key factor which reduces the reliability of a system is related to conveyor transfer points, because of, they can lead to a lot of unscheduled maintenance. But a lot of the time too, when it comes to designing transfer points, especially when you have greenfield applications where you're sort of starting new plant design from scratch, is that in some circumstances the design and positioning of conveyor transfer chutes and stations are sometimes overlooked, or not enough detail is given at the early stages. So sometimes, head pulleys and conveyor systems are locked in the design, but they may not necessarily be in the right location for offset or overall height. They might be too short, or there's excessive height. So, we typically want to start designing and considering transfer chutes in the early stages of the design process. So let's just take a look at this example. So this is a conveyor transfer point handling very sticky and wet bauxite, feeding into a screening plant in a washery. So this transfer chute requires water to be injected into the product for part of the processing, but also to aid in the material flow. So this material is very, very sticky, at the optimum moisture content. So what happens with this material? You've got a conveyor feeding in, and it discharges into this bottom receiving conveyor. But often it can block. You can see there's a lot of material build up, a lot of choke points for build up to occur and blockages to occur. So typically, if it may take half an hour or so to isolate this equipment, to clean out the chute and to restart the operations. So if you're having around about 70 blockages per year, which was occurring in this example, and your throughput is approximately 4,000 tons per hour with a commodity price of around $70 per ton, then if you have a look at the total downtime and the cost associated with the lost product, you're looking anywhere around about 10 million Australian dollars in terms of lost product. So with this transfer chute, we were able to conduct some comprehensive material testing and modeling to redesign a new chute. And this sort of cost for this process was around about 500,000 Australian dollars. So you can see there that, with this investment, there was a quick return on investment for this operation. So you can see there that the cost can be quite phenomenal for a poorly designed and operating chute. So what are the key design requirements when it comes to chutes? Often we want to have smooth and consistent flow through the chute. So we basically want to manage that material flow from the discharge point from a conveyor onto the next feed point on another conveyor or another bit of equipment. We want to ensure that we have central feeding on the receiving conveyor. So this is why it's quite important to get all the geometry, material trajectory right to ensure that material is centrally loading on outgoing conveyors to minimize any spillage, segregation, belt drift issues. We want to also minimize dust and spillage from the chutes. We want to minimize impact on the chute structure itself, but also conveyor structures to minimize any damage. So if we have high amounts of impact, then we can potentially damage the idlers or the conveyor belt itself, which can be quite costly. But we want to minimize belt wear and tear. Some applications too, you want to minimize any particle degradation. So we need to softly handle that material to minimize impact and degradation and breakage from harsh handling of that bulk material. We also want to minimize any vibration and noise. Quite often when you're dealing with a lot of primary crush or secondary crush products, you're dealing with a lot of large rocks, and these can be quite noisy when they are conveyed and pass through that transfer point. We also need to effectively clean our conveyor belts at the head pulleys to minimize any carryback. So we have to think about how we're going to handle the scrapings and the material from that is stuck to those conveyor belts. Most importantly, we want to make sure that we design our chutes for ease of maintenance. So a lot of the time, often I see that sometimes some chutes are just quickly designed without detailed drafting and thought in terms of how they can be further refine to make them easier to, replace critical wear liners or components. So sometimes we can use, modular chute components to quickly swap out critical parts of that equipment. We also want to minimize any unnecessary drop heights. In some circumstances, we want the drop height to maximize material velocity and keep the chute slopes high. But, there's a certain point. We don't want to be too excessive on that. Otherwise, it's just going to generate more wear and tear. We also want to keep our chute design simple. Sometimes some designers get a little bit creative on the chute designs with playing around with the geometry to optimize trajectory. But, when you're dealing with difficult products, that can sometimes be problematic in terms of, great propensity for blockages and reliability issues. We also want to make sure, we have sufficient slopes to minimize any buildup and blockages of our chutes. But in some circumstances too, we also need to think about, restarting a conveyor belt system if the chute fills up with material to act like a storage vessel during an e-stop sort of scenario. So we need to ensure that when we start our conveyor, that material will draw out of our chute if it's been designed, to act as like a surge bin. And we also need to ensure that we have, sufficient cross-sectional area within our chute. So you need to remember that, conveyors and transfer chutes are volumetric conveyors. Okay, everything is designed essentially on cross-sectional areas. So we just need to ensure that our volumes of our chute are sufficient to minimize any sort of choking and blockages. So what's some of the design philosophies? Often quick solutions are preferred, but they can sometimes be problematic. So sometimes you need to invest a little bit of time and use some simulation resources and analysis resources to evaluate the performance of your chute. In some circumstances, for people that are that are not necessarily designing chutes all the time, I think that transfer stations are quite simple to design compared to other more complicated mechanical systems. However, they're typically the sore point of a conveying system, and typically tend to be the higher failure points in a conveying system. So it's quite important not to sort of underestimate the difficulty sometimes designing transfer chutes. So especially when you have very constraining geometry and especially with sort of brownfield applications where you might be redesigning a system for increased throughput or different material. You have restricted drop heights, or you have structural components in the way that make it difficult to redesign a chute. So this is why it's quite important where in those sort of circumstances to use simulation tools to help with that process. A lot of the time, the selection of the type of chute that we will use for the transfer points will be very dependent on the material characteristics and belt speeds and throughput. And in some circumstances, you don't necessarily have to do really long and detailed analysis of your chutes, but you just need to have a good understanding of the basic principles of chute design and material characteristics. So that's quite important, that last point about material characteristics, because a lot of the time is you need to really understand the material properties in terms of moisture content, how it's cohesive behaviors to really select the right type of chute and all the sufficient slopes that you require to minimize any blockages. Attention to detail is very important as well, because a lot of the time it's like little things with the design of your liner packages with leading edges and gaps between liners, impact angles, material trajectories, handling fines and things like that are quite important, because those sort of things can lead to blockages and underperformance of your transfer stations. You also need to consider the mechanisms of flow. And what I mean by that is the principle of your chute design relying on material sliding on a smooth wear liner or sliding against itself? So they will have different, failure envelopes. Obviously, material will flow a lot more easily on a smooth wear liner compared to, shearing against itself. But in some circumstances, that can be advantageous to minimize wear. And also mentioned before, the actual layout of the transfer point is quite important, during the design of the belt conveying systems. So if we just quickly look at the typical sort of conveyor system, they will consist of a tail pulley and a head pulley, and we have a load point. In some circumstances, we may have multiple load points and multiple loading chutes to feed material onto that conveying system. So once material is fed in on that conveyor belt at the tail end, it is conveyed and transported up to the head end, where there is another discharge point or unloading point with another transfer chute. Okay, so what we're talking about in this webinar is, really dealing with the design of these feed points and also the head chutes as well. We may have intermediate discharge points, such as, with the use of belt plows or tripper conveyors as well. So we have a look at the possible flow, the possible flows and mechanisms within conveyor transfer. Obviously we have material that is fed into our conveyor transfer. And then ideally, we want 100% of that material to be discharged from that transfer chute to maintain continuity. However, in reality, we have to deal with other things like with carryback. You get a small proportion of very fine material that will adhere to the head pulley, carrying around that head pulley and back on the return side of that conveying system. Which is not ideal. So what we need to do is, implement some cleaning systems to remove those fines and that material from the return side of the conveyor. But that material needs to go somewhere, and we need to think about how we handle that product in terms of, do we, let it flow back into the transfer point, or we use a separate method to remove that carryback. We also have some spillage that may come from, the skirts and covers, or even just from the chute itself. So we need to, minimize that. We also have dust that might be emitted when handling dry products. So we need to, contain that dust within the transfer point. We may also have material buildup when dealing with, cohesive and highly cohesive products, which can be quite problematic, because if your mass out is less than the mass in, then over time you will have a potential blockage of that transfer station. So we need to minimize that buildup. We also need to think about airflows. So as material is conveyed into that transfer station, it will induce a component of air, and that will generate air from displaced air, or potentially entrained air from free fall. So we need to minimize the air generation, because that will affect the amount of dust generation. We may have need to implement systems like a local exhaust system or dust extraction system to control that air and dust. We may also use some passive control methods to basically keep that dust within the system and get it to fall back onto the bulk material or the outgoing conveyor. We may want to use water sprays to contain that dust. So we need to think about, how the performance of the water sprays may affect, material flow. If you use too much water, then it may lead to buildup. So what are some of the typical problems associated with chutes and conveyors? So these are the sort of things that we need to deal with on a daily basis. As I mentioned before, we need to constantly deal with fine material sticking to the conveyor. So you see this photo on the top left here. You can see that there is a lot of material that is sticking to that conveyor belt, whereas the coarse material is basically free flowing or following a separate trajectory. So essentially here we have two different trajectories to deal with the coarse material and then that really fine material. We may have issues with, off-center loading. Off-center loading is not ideal because it can typically lead to belt drift issues and spillage problems. So we need to basically minimize that, especially when loading onto the conveyor belts. But also sometimes, that can cause some flow problems if material is fed into that transfer point and it's off-center or it's, potential segregation, as you can see on the top right-hand side here. So segregation can be problematic as well. You don't have sort of uniform flow through your chute. In some situations too, we need to deal with, very large rocks, ROM material. So that, typically you get large rocks sitting on conveyor belts and, that will present some unique trajectory issues and flow issues within your chute. We may have issues with, high skirt wear or, boiling or building up of material in the load zone, liner wear and damage, issues to do with material surging. So in some applications, say for example, with some reclaiming and loading systems, that you get this sort of surging and plugging effect that can occur. So we need to model and design appropriately for chutes to be able to handle those surges. And a lot of the time, one of the biggest problems is just material buildup, as shown in the bottom right here side. You can see there that you get a lot of fines that will build up in a chute and eventually block it. So one of the big problems associated with a lot of chute blockages and flow issues is typically around the fines and segregation of fines in a transfer point. So you can see here in this example that we have fines coming off the scraper, which is building up on one side and eventually choking the chute. So there's things that we need to do to try to minimize that. That buildup can change the trajectory and flow behaviors and performance of that chute over time. So, we need to think about how we can, minimize that, the segregation of fines and the fines that are placed into the transfer stations. So some of the issues that can occur is you get that buildup and it gradually will grow over time and lead to, unfavorable flow patterns or preferential feeding through the chute and onto conveyor systems and equipment. And often, sometimes what happens is the throughput of that system needs to be reduced in order to minimize any blockages. So here just shows some examples of what can happen, when you get the buildup of fines in a chute over time. You can see there you get these unique flow paths that are generated and large volumes of material that build up, and cleaning these volumes of material can be quite difficult, time consuming, and there are safety issues associated with that cleaning process. Even sometimes when that material dislodges naturally from the chute, you may get this large slug of material that will just be conveyed along the system, which may cause some blockage or plugging issues downstream. So we do need to model and monitor these fines quite carefully. So how do we avoid the problems? There's a lot of things that we can do. We can sort of follow these steps here, and a lot of the time is due diligence and knowledge of the products that will be handled. So I'll iterate that a couple of times. Is it's quite important that we understand the material characteristics and don't make assumptions. Just thinking, for example, coal is coal. It's quite a forgiving product to handle. Or iron ore characteristics, for example, are quite consistent. They can vary a lot of in a lot of operations, and this can be quite problematic to the long-term performance of equipment. We also need to evaluate the trajectory of product through the chute. Okay, to basically, obviously we're trying to redirect that product onto an outgoing conveyor or another bit of equipment, and we want to basically control and centrally load that product. So we need to understand where that material is going to flow through the chute. We also need to control and manage the flow in terms of, containing that product, trying to minimize any sort of spraying and proliferation of product as it is conveyed through the transfer station. We also want to regulate the material velocity. So we want to maintain a minimum velocity to make sure that material continues to flow, but we don't want that velocity to get too high where it will start to cause a lot of spillage or wear issues. And it's quite important that we model and understand the presentation of that material on the outgoing conveyor belt. And this is where DEM and simulation tools are very handy for that, because they provide that 3D visualization capability. So a lot of the traditional analytical models are very limited to two-dimensional, and it doesn't really provide that comprehensive assessment and visualization of how the actual materials are flowing through the chute and presenting on the outgoing conveyors. And it's quite important throughout this whole process is to conduct our design checks like what we do in other engineering processes. So we can use things like continual modeling and rules of thumb, discrete element modeling, which is quite handy because you can do a lot of iterative designs in a virtual environment. So you can look at a lot of what if scenarios, really test out that design. And I suppose one of the good things about DEM modeling is that because of that ability to visualize the material flow, it's very handy when presenting your design solutions to senior management or the key stakeholders to provide confidence that this solution is going to work as predicted through your design process. We can also conduct scale modeling, where we just build small scale, physical equipment to examine the performance of the chutes. But these can be quite time consuming, and they become quite limited in terms of the type of materials they can reliably model. So nowadays we have a lot of simulation tools at our hand that we can use in the process of designing and optimizing our equipment. So these tools include things like discrete element modeling to model and simulate material flow behaviors. We can also couple DEM with finite element modeling to look at the structural response and strength of our critical equipment. So that's a good thing with DEM coupled with FEM, is that we can take those loads from our bulk material modeling and use them for our finite element modeling, so that we actually have some representative load cases. We can also use multi-body dynamic simulation if we wanted to look at some complex mechanisms that we may need to model. And we can also utilize computational fluid dynamics to look at things like the interaction of your bulk material and airflows to do some prediction on, generated air through that conveying process, and also, for example, where air will flow and things that we can do to try to minimize the air generation mechanisms. So there are various, analytical and traditional methods and models available, and this is what I will cover in the next few slides. So we have various models that look at the discharge of material from our feed conveyors, and then we have various trajectory models and impact models. We have hood and spoon, or examining the flow of material through our actual chute, like in terms of curved surfaces or straight inclined chutes, so we can calculate the material velocity, the height of your material stream. So yeah, there are various chute flow models available that can be conducted, that can produce results very quickly. But also with these models too, we also need to, in some circumstances, understand, for example, if we have large rocks and oversized material flowing through, and how our chute will perform with the effect of lumps. Okay, and this is where DEM is really good for this, because it makes it a lot easier to model the effect of lumps. So when it comes to discharge trajectories and considerations, sometimes the discharge trajectories can be a little bit complicated to assess, especially for low speed conditions where the material wraps around the head pulley. So there are various considerations that we need to take into account. For example, you might get some divergence of material as it discharges off that head pulley, so the material width may increase. And you can see there, you get this sort of shedding effect as that material accelerates, so that can change the trajectory profile. We also have to have a look at the effect of, for example, lumps, and in moisture on the trajectories, and also other things to do with, like, surges, what's the sort of upper and lower bounds of our trajectory models. So there are various trajectory models that are available, and there's a good overview of these models by the work of Dr. David Hastie, that compares the various trajectory models that are available for designers to use. So there are, some of the sort of common models are, the SEMA model, Dunlop, Booth, and Golka. So this little table on the right here just shows some of the capabilities of the various models. So some models are quite simple, and other models like the Corzen and Golka model are a little bit more complicated in regards to evaluating the trajectory using those models, but they also consider a lot more variables as well. So when it comes to calculating the trajectory, it's quite important to understand the material profile. So we have to understand the depth of the material on that conveyor, and also the width of that material when we are assessing the trajectory. So this obviously is quite handy for, one, assessing the discharge trajectory, but also the width of any deflector plates or our chutes, to ensure that it can capture that bulk material. So there are things that we do need to consider, things to do with, like, belt drift. Sometimes you'll get the belt drifting, the material will offset a little bit too, so that will change how that material presents into the chute. We have to look at things like surges, potentially flooded belt scenarios where we have a very large depth of product on the belt, and belt transition effects. So as that material comes up from the full troughs and transitions to the flat section on that head pulley, that angle at which it approaches that head pulley is quite important. So you can see here, if we have a look at some of the effects of the transitions, the material flow behaviors. So on the left-hand side is just showing quite dry and fine material there, and then on the right you've got quite wet and sticky ore, and you can see there you start to get this sort of cracking and separation of that material on the conveyor belt. So we need to take that into consideration, with any sort of chute design. There are other things too that we need to look at in terms of the transition support. So sometimes some conveyors are not well supported in that transition zone. So what can happen is that belt will sag, and that essentially changes the angle of approach of that material as it comes up onto the head pulley, which will change the discharge angle and the trajectory of that material off that conveyor head pulley. So you can get like that little bit of a ski jump effect with excessive belt sag on that transition. So ways that we can calculate the cross-sectional area of that material profile on the feed conveyor, we can use methods like that presented in SEMA 6. So here's just showing some of the calculations that we can conduct to assess the depth of material in the full trough. So essentially what we're doing is we're just looking at the material in the full trough, because essentially as that material flattens out, the depth of the material in that center part of the belt doesn't change too much. But then as that material flattens out too, we also want to examine the edge clearance from the edge of that material to the edge of the belt, because that will basically govern the width of the material as it discharges off the head pulley. So we can use these equations to evaluate those critical parameters. And then what we need to do is, we need to assess the discharge trajectory at the centroid. So with a lot of these calculations, some of them consider the velocity at the top of the belt, others consider it at the center of gravity. So with the SEMA calculations, it's based on the center of gravity or the centroid of that material profile at the head pulley. So essentially, we need to calculate that velocity at the center of gravity, and we can use these equations that are shown here. So essentially, what we need to do is once we calculate that material velocity at that centroid, we need to conduct a speed check. Okay, so essentially what we want to do is assess is that trajectory what we call low speed or high speed trajectory. So if it's low speed, essentially the centrifugal force is quite low and that material will wrap around the head pulley to a certain degree. And we can calculate that angle of discharge where the material will remain in contact and that discharge point using this method. However, if the speed check is greater than 1, what that means is it's high speed trajectory, and that material just discharges at the discharge angle of in that transition zone. So basically, the material leaves tangentially to the conveyor belt. So here just shows the example how we can plot it using the SEMA method. So what we do is we calculate we do that speed check. And this is an example for low speed trajectory. So we calculate that angle of discharge. And what we also need to do there is work out where the centroid and the depth of that material bed. And then from there, we draw a tangent line from that centroid, it's 90 degrees to that angle of discharge. And then what we can do is we basically put intervals there of 50 millimeters per meter per second of your centroid velocity, and then just doing your standard trajectory modeling. What we need to do is basically draw down lines. You can use the table provided in SEMA for each interval in terms of that actual drop. And then from there, we just basically work out and plot our trajectory at the centroid. And then because we know the depth of that material, we can also draw in the upper and lower bounds of our trajectory. Okay, so that's a typical way that we calculate our trajectory. So if it's a high speed trajectory, that angle of discharge will essentially be 0, and that material would discharge tangentially to that conveyor belt. So here just shows the comparison of a low speed versus high speed with the various models. So for low speed, there is a little bit of deviation between the different models, and that's because of the angle, the discharge angle that is calculated. They do vary a little bit between the various models, and this is where low speed trajectories tend to be a little bit more challenging compared to the high speed trajectories. With high speed trajectories, you get that material basically discharged in the tangential point, and you can see there the models are quite similar to each other. And a lot of the time with our transfer chute designs, the material is only discharged for a relatively short distance from the head pulley. So when you look at the upper section of these trajectories, they are quite similar to each other. So years ago, we did some research and validation at the University of Wollongong to basically examine different trajectory models and chute flow models and compare them to analytical models as well as for DEM validation. So we essentially just had this conveyor system set up to recirculate material at different velocities And this is where we could do some, design checks of and validation of the various trajectory models. So here just shows the experimental results where we modeled the trajectory at a belt speed of 1 meter per second, 3 meters per second, and 5 meters per second. So you can see here from these trajectories, especially at the high speed, you start to get a little bit of divergence of that material. Okay, so it's quite important that when you're modeling these trajectories, especially in DEM, is that the material, when it discharges from that conveyor belt, that the slip's velocity is is zero. Okay, the actual material is discharging at that belt velocity. Okay, so from this work, we were able to compare those experimental results to the DEM results to the analytical models there, and you can see there with a lot of these models that the SEMA method and the Dunlop method, which are very similar, compare quite well to the experimental results. And then when we compare the experimental results to the DEM, you can see there that we get a good correlation between the various models at the various speeds. And you could see there from the previous slide there, at 5 meters per second, you're getting that fanning and dispersion of that material flow, which was captured here in the DEM simulations when we look at a slice through that center plane. So where it gets a little bit more complicated is sometimes when we introduce lumps. Okay, and this is where DEM is quite good. So when we have quite slabby or large rocks on top of that material, it can create some unique challenges with modeling that trajectory, because that material, those lumps will sort of have their own trajectory, and that sort of the upper and lower bounds of that trajectory can vary depending on the characteristics of those lumps. And this is where DEM can actually model those that lumps and the shape effects, and to more reliably and accurately predict where that material is going to flow. Another challenging application when it comes to trajectories is when we're dealing with apron and belt feeders that operate at low speed but very high material depth. So you can see here's a sort of the conventional sort of outline of trajectory. If you were, assuming that, this point here is the depth of that material from the belt feeders or the apron feeders. But in reality, what happens with these high depth material beds feeding off these slow feeders is that material tends to, shed, close to the effective angle of internal friction at over the head sprocket or head pulley, and so it actually changes that material trajectory. So this is where a lot of the continuum methods and analytical methods sort of struggle to predict that behavior or slip. Okay, whereas DEM is able to model that behavior quite accurately and effectively. So when it comes to sizing, conveyor transfer chutes, as I mentioned before, they're volumetric conveyors. Okay, so what we need to do is essentially calculate, the cross-sectional area of that bulk material on that feed conveyor. And a good rule of thumb is that, the cross-sectional area of your chute is approximately, 4 to 5 times the cross-sectional material of the product on the feed conveyor. Okay, so if we get, especially we're dealing with sort of low density materials, or even quite sticky materials, we need to ensure that that cross-sectional area is sufficient to avoid blockages. So let's just talk about some of the traditional or the types of conveyor chutes and stations that are typically used in industry. So some of them include like a rock box or cascading type chutes that essentially have ledges of varying size and design configurations to essentially hold your bulk material. And the aim of this is to basically promote a flow mechanism where material is shearing against itself. So these can be quite good in terms of, when you're dealing with quite coarse and abrasive materials, basically let the material slide against itself. But in some applications, rock box and cascading chutes can be quite problematic in terms of, material build-up and blockages. Okay, so you really do need to, select a low cohesion material, and ideally stuff that has a low fines content. Like you can design these for, materials that have a lot of fines, but they can be quite problematic if that moisture content starts to elevate, and that material goes from a sort of a good to handle to challenging or more difficult to handle moisture state. Okay, so that's why it's, you need to be careful when using, rock box and cascading chutes, for very, very sticky materials. But in some applications, when you're dealing with primary crushed rock that is, quite bony and dry, these are fantastic chutes because they can, minimize, noise, minimize wear and tear. They can control the velocity quite well. They're very good in terms of being able to deal with, changes in flow rates and in belt speeds. So if you get surges coming through or you want to slow the conveyor belts down, they can typically have some degree of turn down and still optimize and work in an optimal state. Another typical design that we see with a lot of very fine and sort of cohesive products is the use of hood and spoon type designs, okay, where on the left here just shows an example where we have basically a hood or deflector plate at the top that basically intercepts the product and then redirects it into the lower chutes. So there's typically some chute work. We may have, diverters or, flop gates in between the head pulley or feed conveyor and outgoing conveyor. And then at the bottom here, we typically have what we call a soft loading spoon. So the idea with these types of chutes is that it basically controls that material velocity, keeps the material crowded, regulates the material velocity, and we can basically design the radiuses and the slopes of that to regulate that material velocity. So you can see on the right here shows an example of a large, drop height chute that was approximately about 30 meters high. And with this careful design, we can sort of snake these chutes in order to regulate that material velocity. So we basically accelerate and deaccelerate that material to keep the velocity within an appropriate boundary. However, one of the problems with these types of chutes is that naturally to promote flow, you need to have material sliding against your wear liners. So they do have a tendency to experience higher wear and tear. But, this is where we need to use essentially good wear liners to minimize the wear. So essentially the design or the philosophy with a hood and spoon design is that we have a deflector plate or a hood, which basically captures that material as it discharges off the head pulley. And then what we want to try to do is, converge or contain that material and redirect it vertically into the lower chute. So the good thing about deflector plates is that they're good because you can adjust the trajectory, in order to line up that material ideally onto the lower parts of the chute or onto the outgoing conveyors. But with these types of chutes as well, they do have a sort of a narrow operating band in regards to, you can only have small amount of, change with the belt velocities because it changes the trajectories and the impact angles on the deflector plates. But as I mentioned before, wear and tear can be a problem with quite abrasive materials. So we need to be careful with, selection of liners. Ideally with these types of chutes, we want to keep the impact angles less than, 30 degrees. Ideally, somewhere between less than 10 degrees when dealing with really sticky materials. And we also want to ensure that, we keep the chutes are large enough where we know typically we're not filling more than, a quarter of or a third of that chute. And we want to basically maintain, rapid flow conditions where essentially the depth of that material is less than the width of the stream. And we can, converge, the sidewalls or some of the chutes to try to contain and sort of compress that material to a certain degree. But we, in some circumstances, we've got to be careful with the amount of convergence that we do provide. Otherwise, we can, cause material buildup or chute blockages. So here just shows the example with, a design of a deflector plate or a hood. Typically we need to do our trajectory modeling to position that chute to obtain a low angle of impact. And ideally we want to, discharge that material vertically into the lower chute. So sometimes if these are not designed right, you might have a little bit of, lateral velocity, which can kick the material out and lead to some problems, in the lower parts of the chute. Okay, so with these types of deflectors as well, we do need to be careful. Some people sometimes put deflector plates a little bit too close to head pulleys. So like in some situations, yes, you can put them close, but you need the right conditions, and you need to be very mindful about that, because if you get too much build up around the impact point, it can choke the chute. So if you move the conveyor or the head pulley, the deflector plate away from the head pulley, you provide a little bit more breathing room before you'll see any sort of blockages occur. We also need to be careful of lumps. So we need to provide sufficient gap to make sure that the lumps can flow through. And we also want to ensure that, things like foreign objects like roof bolts or, sticks or slabby material can flow through. But we also need to design and be mindful of, surges that may occur as well. So here just shows the example from the conveyor research facility, where we're looking at the flow of material with a belt velocity of 2 meters per second. And you can see in this setup here, we have a very low angle of impact, which is ideal. And then we have material discharging vertically from that deflector plate. However, it's quite important, how you position the deflector plate in terms of the material flow behaviors. So you can see here shows a comparison at 3 meters per second, where we have the deflector plate positioned in a way with a higher angle of impact on the left. And you can see what happens is when you have a high angle of impact, you get a little bit more spraying of material, which can be problematic because you can lead to build-up of material in the lower parts of the chute. Then on the right-hand side shows where we have a very, very low angle of impact. You get that nice acceleration and thinning of that material, but minimal spraying and generation of that secondary flow streams at that point of impact. So it is quite important to to locate these deflector plates appropriately to minimize that dispersion of flow. As I mentioned before, sometimes we have to also be mindful of any foreign objects, like logs and roof bolts, for example. These can cause problems in terms of getting stuck in chutes. They can potentially block chutes, that can rip conveyor belts. So we do need to ensure that these products can flow through the conveyor system well. And this is where DEM comes quite handy, because we can actually model these odd particle shapes very reliably and easily these days using polyhedrals and multi-sphere particle modeling approaches. So here just shows one of the models that are available to assess the material velocity through a hood. This is using Professor Alan Roberts' model, and this is a lump mass and analogy approach. So what we are essentially doing is just modeling a lump of material flowing around that inverted deflector plate. So this lump mass just basically assumes that we have constant bulk density. and it assumes that the material is cohesionless. So what we can do is we can use these equations shown on the right here to essentially assess the material velocity at different angles or positions around that deflector based on the radius and that material velocity once we solve for some initial conditions to assess this parameter, okay. But with this modeling too, we also need to take into account the wall friction between that bulk material and the surface of that chute. And that wall friction can vary depending on the characteristics and the profile of that chute. So what we do is we introduce an equivalent friction coefficient that takes into account the effects of the sidewalls and pressure ratios in that flow channel, and also takes into account, for example, the ratio of that material depth to the width of product in that chute. We can also take into account the effect of converging channels in that effective friction angle. So these models are just used to basically assess the material velocity of that product as it flows around that chute. Now, the other thing to keep in mind is that typically wall friction, especially with slightly cohesive and highly cohesive materials, is that it does vary depending on the pressure. So as that pressure typically reduces, the effective wall friction increases. Okay, so that's why typically what you'll see is that the deeper that material, the lower the friction or the wall friction will be. It's also a very similar concept with the design of a spoon or soft loading chute. Okay, so what we need to do is we are basically intercepting the material as it discharges from the head chute or the feet or deflector plate, and then material will impact the lower parts of that chute, ideally with an angle of impact like less than 30 degrees to minimize buildup and wear. And what we are trying to do with this curved soft loading spoon is basically redirect and point that material in the conveyor direction to softly load that material so that we minimize sort of spillage in the impact forces on that conveying system. So we also have a similar model from developed by Alan Roberts that we can use to assess that velocity in the lower spoon, which is a very similar or same sort of procedure and concept as the hood calculations. So what we are trying to do with when we're designing our lower spoons is obviously we need to regulate the material velocity by changing the radius and the cutoff angle of that chute. Okay, so what we need to do is we need to ensure that the slope at the bottom of that chute is sufficient to make sure that material is not going to slow down too much to start building up, and we maintain what we call these rapid flow conditions where we get that little bit of like thinning of that material flow in that chute. So what we want to try to do is when we're doing these calculations is assess the material velocity discharging from that chute so that the component of velocity in the belt direction is close to matching the belt speed. So that way we have minimal slip and that ensures that we have nice soft loading on that conveyor. So things that can be quite tricky is that sometimes when you're loading onto sloped conveyors, you can get this effect here where we have what we call boiling, where the material just sort of sits there and tumbles around on the conveyor belt, and that can lead to more spillage and belt wear. So this is where a soft loading chute is very handy to basically kick that material forward to minimize that buildup. We also have analytical models as well that we can assess the velocity along just straight inclined chutes using the equation shown there. And essentially the same principle is that what we want to do is ensure that material is accelerating along that inclined plane. So if the material starts to deaccelerate too much and the depth increases, it's a potential stalling point, and you could get material that blocks that chute. So there is a limit of how long that straight incline section can be before you get a blockage. We also have impact models. So if you wanted to assess the velocity of material, before and after impact, say for example on an impact plate or a deflector plate or a lower part of your chute, there are models by Arnold and Hill, and also Stewart, Dick, and Royal that you can use to assess the velocity VA after the point of impact. As I mentioned before, belt cleaners are quite important and a vital part of any conveying system, and we need to basically design for those fines. Okay, we need to think how those fines will be handled from the scrapers. So sometimes that material can be thrown back into the center of the chute, or in some circumstances we may add some water and we use maybe a separate dribble chute or chute that takes those fines out of that transfer station and then either feeds them back onto that receiving conveyor at a different location. So when we look at the profile of our chutes, generally what we want to do is introduce some fillets or radiuses in the corners to minimize buildup, to encourage central loading, and also a good surcharge angle on that outgoing conveyor. So it's quite important, especially when you're dealing with very fine and cohesive materials, is to either place a fillet or radiuses into the chute corners to minimize buildup. In some very free flowing and coarse products, yes, you can get away with having square corners, but yeah, if the material is slightly cohesive, then it's quite important to place that detail into the chute designs. So here just shows an example where you can see at the part of this spoon where the upper section there was some fillets that were placed into the chute, but they got missed in the lower sections of that chute. And you can see what was happening quickly. There was continual buildup that would occur in those corners where there was no fillets. So what they did is they had to go place the fillets back into that chute where they were missing. And once they did that, they basically reduced the amount of buildup that was occurring. So the fillets and radius in the corners are very important. So when it comes to wear liners as well, there's a wide range of wear liners that are available. Typically, they might be sort of products like metallic, like sort of chrome and carbide, or like white iron type products that are quite ideal for dealing with a lot of impact. So in impact zones with like coarse rock, you may use those type of products. If you're trying to minimize wear due to sliding and abrasion, ceramic tiles are very robust and ideal for those types of situations. But ceramic tiles are quite brittle, so you need to be careful with the selection of the type of ceramic tiles and the location and the fitting of those tiles to minimize any breakage of the wear liners. So generally, what we need to do is to minimize the wear and tear and damage. We do need to design for a certain impact angle. Ideally, with ceramics, you want to keep that impact angle as low as possible to reduce, impact wear. But with like steel or metallic liners, we can, have a slightly higher impact angle because they can sustain a little bit more direct impact. So, design of skirts and the loading zone is quite important, to minimize any spillage issues. So this is quite important when we are doing a lot of the chute designs, that we do spend a little bit of time detailing up around the skirt zones. So in some situations where you may have direct loading or, poor chute design, sometimes people just load product directly onto a conveyor belt and let the skirts do the work. However, in that sort of situation, what can happen is you can generate a lot of belt wear and skirt wear around the skirt line. So that's why it's quite important to do a lot of good modeling and use some good design practices when designing your chutes to softly load and control that material profile and presentation on the outgoing conveyors, to basically ensure longevity of your skirting systems. So a lot of the time when you're designing chutes, you really want to try to minimize the amount of product that is rubbing against the skirt plates. So in this second half, I'd like to introduce more advanced simulation tools within the RTS suite that can be used for design optimization and validation of your chute designs. So here you can see some examples of some EDEM simulations of various transfer chutes. So the left-hand side here just shows you a primary size, a discharge chute, and on the right-hand side is a rock box type chute. So you can see with DEM, it allows us to provide 3D visualization of material flow to assess things like the particle velocity, trajectories of material, the effects of, for example, lumps and coarse product on material flow, and also assess the presentation of material on the outgoing conveyor. So you can see with this tool, we're able to import our 3D geometry of our chute design and then verify that performance and of that chute and see if there's any potential optimization. So that might include some tweaking of some geometry to improve the presentation of product throughout the chute. So what's important with any DEM simulation is actually development of a calibrated EDEM material model. So you can see there on the left-hand side, there are various properties and attributes of our granular materials that we need to model within our DEM simulation. So there are things like interaction forces, material properties, and morphology like shape and size. And we can take these attributes into consideration with DEM modeling by considering things like the interaction and contact forces between particles, also considering things like particle shape and size distribution, and mechanical properties like solids density and shear modulus, or the stiffness of our particles. So particle shape is very important when it comes to DEM modeling. As you can imagine, in a lot of real life applications with primary crushed product or runoff mine material, the particle size, the particle shape isn't spherical. Most particles are generally quite irregular in shape and angular as well. So we need to actually take into account those geometric properties of our particles, and we can do that in EDEM by using particle shapes like these multi-sphere particles or the polyhedrals or spherocylindrical particles. By introducing these non-spherical particle shapes into our simulations, we can better model real life particle impacts and interlocking as well. So the good thing with the multi-sphere approach is that it provides good computational efficiency and provides sufficient interlocking and non-sphericity within our particles. So the other important aspect with the modeling is actually the consideration of the contact mechanics between particles and between particles and your geometry. So EDEM has a wide range of inbuilt particle models. These can be consider non-compressible or incompressible materials as well as compressible materials. So in some circumstances where you might have quite free-flowing and coarse and bony type product, you can get away with just modeling these particles using a Hertz-Midler model. But with a lot of cohesive and wet bulk materials, we do need to consider that cohesive behavior between particles, and that's where we can introduce things like the Hertz-Midler with JKR, the Edinburgh elastic plastic adhesion model, hysteretic spring model, or even if you like, you can introduce models like the liquid bridge model. And these actually take into account the sticky behavior of our materials. And then we also need to take into account some rolling friction to do with the asperity and aspect ratios of our particles, but typically by introducing some non-sphericity with multi-sphere particles, there is a lower reliance on these rolling friction models. And then the other things that we can do within EDEM is modeling particle breakage as well. So if you want to look at breakage and attrition as materials transferred between conveyors or between points, we can model that as well. And we can also model wear. So I'll talk a little bit shortly about some of the wear models within EDEM. So one of the important aspects when it comes to DEM modeling is actually the speed and accuracy of solving your simulations. So there is quite a bit of computational overhead, especially with large DEM simulations due to the large domain and the large number of particles. So within EDEM, we can utilize a Chute solver. So by using a GPU solver, we can solve our simulations much faster. So within EDEM, there is a couple of options here within the solver where we can change the precision mode of our simulations. So this allows us to adjust things like the accuracy and the speed. So if we want a highly accurate simulation, we could use double precision, but this will require longer times to solve your simulations. But in most circumstances, we can use this hybrid mode, which is a nice balance between accuracy and speed. So you can see here on the right-hand side, here just shows a sort of typical sort of speed up we expect with using the Chute solver to solve a transfer chute between CPU, Chute in hybrid mode, and Chute in double precision mode. And you can see there the speed up between the hybrid and double precision, and especially between the CPU, is quite noticeable. And this will all depend based on the specifications of your GPU card. So another important element within modeling complex transfer chutes is the ability to model multi-physics. So we touched on this before about the ability to couple DEM simulations with other solvers. So if we wanted to model, the say mechanical mechanisms that may be within a transfer chute, say for example, if we had a flop gate or an adjustable deflector plate, and we wanted to model the force and the torques on those critical components, we can use an Altair product called MotionSolve, which is an MBD solver. If we wanted to look at the structural performance and integrity of our geometry and our equipment, we can couple DEM with OptiStrut or SimSolid, which is a meshless solver to analyze the deformation and stresses on your critical components. So this is quite important when you want to, ensure that your chute will not, fail or collapse. So we can take realistic loads from your DEM and import them into your FEA solvers. Another thing that we can also do if we want to model airflow is either using a one-way or two-way coupling. We can couple our DEM simulations with AccuSolve, which is a CFD solver within the Altair simulation tools. So this allows us to, for example, model the air-induced flows from material flow. And the other advancement that we can do is to enhance the design cycle is by utilizing AI tools. So we could utilize tools like HyperStudy, which is a design exploration tool that allows designers to improve their designs, but also look at the inter-parameter dependencies in a much shorter time frame. So we could use this tool, for example, if we wanted to adjust, the position of a deflector plate to ensure that we have central loading on our outgoing conveyor belt. And this is done by using a connector between HyperStudy and EDEM, which is called the EDEM HyperStudy connector. So wear modeling is very important when it comes to chute design. So especially when you're dealing with a lot of self-cleaning type chutes where you have a lot of material flowing against your wear liners, it's to be expected, depending on the abrasiveness or your material, that you have a potentially a high amount of wear in certain regions of your chute. And we can model that within EDEM to find these hotspots and also help design the wear packages in terms of selecting the right type of wear liners for different types of impact and abrasive wear, and also work out sort of what sort of thickness that we require to obtain a certain throughput before the wear liners need to be replaced. So within EDEM, we have a couple of different options for modeling wear. One is using the relative wear model that just looks at the dissipation of energy between the particle to geometry contacts. But we can also use normalized wear models like the Archid wear model and the Ocker wear model to model abrasive and impact wear respectively. So this allows us to quantify in terms of absolute wear, in terms of millimeters, due to that particle to geometry interactions. And with this process, we can also model wear deformation as well. So as you get erosion, we can actually model that deformation of that geometry over time and see how that will affect the material flow. So here just shows an example of an industrial transfer chute that was redesigned using EDEM, where modeling was conducted. So we went back after some period of time after operation of this chute to examine the wear patterns and verify them against the DEM simulations. So what we did, you can see here we have this deflector plate or hood and spoon type arrangement chute handling abrasive bauxite. And what we did was we modeled the abrasive wear with the Archid wear model and the impact wear with the Ocker wear model. And when you compare the wear patterns on the actual deflector plate, you can see there around that impact point, there's a high amount of wear, which aligns quite well with the impact wear model from using the Ocker contact model. When we also look at the lower spoon, you can see there when we compare the real life wear patterns, you can see there that there's like a kidney shaped profile around that impact point and a lot of wear around that transition where that chute kicks. So when you compare them to the DEM simulations, you can see there that the wear patterns are very similar around that impact point with that curvature there, and also around that transition where the deflector plate kicks. And you can also see there on the skirts, there's that leading edge on the skirts is also experiencing higher wear. And you can just see that in the photo here on that bottom edge there, that was experiencing higher wear. So another important element when it comes to designing transfer chutes to minimize dust generation and also to evaluate the performance of any dust extraction or suppression systems is to model the airflows generated from the material flow. So within EDEM, within the RTS suite, we can couple EDEM with AccuSolve to model the airflows within a transfer chute. So if we look at this typical example here with sort of self-cleaning hood and spoon arrangement chute, what we want to do is actually quantify the volumetric flow rate of air and the velocity of air throughout this transfer chute, especially in the stilling chamber, so that we can design our dust extraction system in terms of what sort of volumetric flow rate of air we require, what sort of velocities are expected in this stilling chamber. But we can also look at the effects of, for example, any sort of baffle plates or dust curtains that may be placed into the chute to try to slow down that airflow. So here just shows an example of a two-way coupling between EDEM and AccuSolve, where we're actually modeling a transient type simulation here with material coming into that transfer chute and then reaching steady state flow conditions. So on the right-hand side here shows you the velocity of the air throughout that transfer chute. So by using these simulations, we're able to gather some information here about like the air velocity at the discharge of the chute, the pressure at the inlet and the outlet. So you can see there that with this simulation, there's a peak that occurs or a surge that occurs as the material starts to flow through the chute. So that's that air that's within the chute being displaced. Then once we hit steady state conditions, you can see there that air velocity starts to reduce down to a steady state velocity and also volumetric flow rate as well. So another important aspect when it comes to verifying the performance of the chute is actually looking at the structural integrity. Okay, so a lot of the time when it comes to chute design, sometimes additional steel is just thrown at the chute to ensure that it will be strong enough to handle the bulk material loads. So these are under steady state loads, but also, for example, the loads when the chute will build up or block, we have to look at those dead loads as well. So what we can do within the Altair suite is actually use EDEM to run a simulation of your material flow and get those contact loads between the bulk material and the equipment surfaces, and then import them or map them into either OptiStruct or SimSolid. So the good thing with SimSolid is that it's a meshless type tool. So what you do is actually just import your 3D CAD models with minimal cleanup, and then we can apply some constraints to it, and then actually model the deformation and stresses. And I'll show an example of this later on. Another thing that we can also do is actually model the stresses, or do a two-way type simulation between OptiStruct and EDEM. So this allows us to actually model the nodal deflections or movement of your geometry. So this is ideal if you have, quite flexible geometry, and we want to examine, the material flow due to that high deformation. Okay, so we can run a transient explicit type simulation to model, the stresses and deformation on complex geometry. So another important aspect when it comes to chute design and also modeling is material testing and calibration of your material models. So we conduct material testing, generally for sort of two purposes. One is to actually understand and quantify the characteristics of that bulk material. As I previously mentioned, is quite important when doing any sort of transfer chute design or troubleshooting and optimization, is actually knowing the behavior of your material. Okay, so we want to, for example, assess, is this a free flow material? Is it moderately cohesive, or is it very, wet and sticky type product? And this will sort of provide some guidance in terms of the types of chutes that we should be using for those type of materials for reliable performance and operation. So what we typically do is, we have a look at our industrial application. We look at the flow mechanisms. We look at the different type of liners that may be used on site, the typical sort of velocities of your material. And then from there, what we do is we collect a representative material. And typically, we need to take these samples either ideally from an inline product sampler, or maybe from a stockpile, but you need to be careful when taking those samples to ensure that they are representative. Then from there, what we do is we will send those samples off to a laboratory, and we'll conduct some material testing. So here's just shows an example of some of the material testing we do for DEM calibration. And then we can use data from these simulations to calibrate the parameters of our material model. So what we will do is, for example, is where we will replicate the simulation or the experiments that were conducted in a laboratory in a virtual environment with our bulk material that's been set up in EDEM. And then basically we will analyze the performance and behavior of that material. So what we end up doing is basically running parameter variation type simulations just to examine the sensitivity of various parameters until we find an ideal set of parameters that matches the physical testing results. So that process is usually iterated until we find the ideal set of parameters. So some of the things that we also do is, before we start doing our material testing for DEM calibration, we conduct some flow property testing. So this may include like using a Janicki shear tester. So what we do with a Janicki shear tester is that we shear this material under various loads and moisture contents to basically determine the sensitivity or variation of internal bulk strength with moisture to determine, for example, the worst case condition. So what we may do is we may decide to conduct development some material models based at these worst case conditions, and either maybe a higher moisture or in most circumstances a lower moisture. And that just typically depends on the operating envelope on the real life industrial application. And then from there, from this shear testing, we can examine the internal flow properties of our material to examine things like the flow function, effective angle of internal friction, and provide some data that can be used for calibration, but also for analytical chute design methods available. So here just shows an example of what we call our rock box test, which is used for parameter calibration. So this is for examining the particle-to-particle interaction. So what we do is place product into this upper box, and then we drain material out of that box, and then material flows dynamically into this lower box, and then we measure things like the drained angle of repose and the dynamic angle of repose in the lower box. So we can vary, the drop height of this material to examine different impact velocities, and also, examine different moisture contents as well. Another important aspect is actually looking at the particle to geometry interactions. Okay, so it's quite important to understand wall friction, especially with self-cleaning type chutes. So what we can do is conduct Janicki type shear tests between our bulk material and various wall coupons. And from this testing, we can examine a variation of the kinematic angle of wall friction, but also assess the varying wall friction angles between different materials to select more appropriate materials, ideally products that display low wall friction. But in some circumstances, we need to use products that display high wall friction because of their wear characteristics. So we need to understand what sort of chute slopes we require to ensure that material will flow through our chute. And we can also conduct some inclination testing. So you can see here on the right-hand side where we basically compress product at different loads onto a wall coupon, and then we incline that wall coupon until product slides off. And we can replicate that within a DEM environment. The other thing we can do is also calibrate our material models from using direct shear testing. Okay, so you can see here within EDEM, by selecting appropriate contact models, we can replicate the shear tests between physical and a virtual environment and replicate things like the effective angle of friction, the flow function, variation of bulk density due to compressibility effects, and then also wall friction as well. So what I'd like to do now is actually provide a bit of a case study to show and demonstrate the utilization of EDEM to examine the performance of a chute, identify problems, and then also, more importantly, examine the performance of some redesign options to improve the overall reliability of this chute. So here shows an example of the chute that we modeled. Okay, so this is a transfer chute that is handling very sticky and abrasive bauxite. So this is like benefied and primary crushed bauxite, and what material is basically transferred from the mine to the port and via this transfer station. So this transfer station has a notable drop height. Product is fed in on this conveyor C6 that passes through this head chute where there is a tramp magnet here to capture metallic or tramp material. And then product is also passes past this product sampler. So this is basically used to sample the product at frequent intervals for quality control. So this is quite important with this transfer chute, is not to actually jeopardize the reliability of the performance of this sampler. And then we have this lower transfer chute here with a series of rock boxes that transfers product or loads product onto this receiving conveyor. Okay, so you can see here that we do have varying belt widths. So the in-feed conveyor is slightly wider than the outgoing or receiving conveyor. And we are dealing with belt speeds ranging from 3.4 meters per second to 4.2 meters per second. And the throughput of this transfer chute is around about 3,400 tons per hour. So here just shows the overall, another photo showing the geometry and the equipment that is around this transfer station. So you can see there is quite a bit of structural steel. We also have other equipment there with the product sampler that we also need to be very mindful of with any sort of redesign. The other thing to note here is the transition length, okay, of that receiving conveyor. So you can see there that the transition length here starts just, right at the end of this conveyor transfer chute. So on the right-hand side here actually shows you the micro-ledge head chute, where we have that product sampler below. So that's the primary cutter that actually cuts through the material at regular intervals. And, we may need to make sure that we keep any sort of redesign, deflector plates or equipment away from this chute. So some of the typical problems with this transfer chute include, the buildup of material in the head chute. And the main problem with this was that you get a lot of, secondary flow streams or roping of material that occurs as material impacts into the head chute. And the problem with these sort of, high impact angle arrangements is that you get a lot of this material that tends to spread down the side of the chute. Okay, so you can see this material that ropes around over the top, and then that typically really results in a very wide stream of material that is free falling into the lower parts of the chute. So you have, material on the edge there that may be actually building up in the lower parts of the chute outside the main active flow zone, so you don't get that gouging effect or scalping effect to clean that product, which can lead to blockages. You can get this bias of flow down in the bottom chute. So what was actually occurring is that material wasn't centrally loaded into the middle of this outgoing belt. So over time, you would get, material building up on one side of the chute that would lead to product flowing towards one side, and then, non-symmetrical loading on the outgoing conveyor. You get a lot of buildup occurring in this chute. So because of that high impact of material into that lower chute, eventually what would happen is material would compress and slowly build up over time and block that chute. So to minimize those blockages, they had to keep injecting water into the chute, which isn't ideal because that obviously increases the moisture content of that material and can it cause downstream problems because you're dealing with more sticky product. But the most important or critical aspect with this chute was that it required the maintenance crews to regularly come and hose out this chute. Okay, so that meant that they had to have stoppages with the operation to hose out the chute, but it also required a lot of man hours per day to continually keep coming to monitor this chute and clean it out. So what we did with this design to start the process of understanding the fundamental problems with the chute was that we developed a 3D CAD model of our chute. So typically what we need to do is, before we start any DEM simulation, is that we need a 3D model of our chute. And this can be, simplified down to just, a surface model of the critical components that are in contact with your bulk material. But we can add some of the chute work required. And typically in this process, what we do is that, we add the conveyor belts and all the other equipment as well in the 3D model. And then eventually what we do is we export those components out of our CAD model package into EDEM. So here's just showing some of the constraints and some of the structural steel around that transfer station that we need to be mindful of with the redesign process. So what we actually did first before we started doing any modeling was that we characterized our bulk material. So we took we collected a sample from site. So you can see there on the left-hand side, actually shows you that that material is, quite sticky and cohesive, and requires a little bit of strength in order to break it up. So it is a problematic material, especially when dealing with sort of micro-ledged or rock box type arrangement transfer chutes. So what we did was we conducted our shear testing. So you can see here on the left-hand side is that we went through the flow property program of work to assess the moisture content that displays the highest internal bulk strength, and also understand the sensitivity of moisture content on the flowability of our product. So what we can do from there is, once we understand what the sort of worst case condition is, we can conduct some further shear testing to develop the flow function and evaluate the effective angle of internal friction. And from there, we can evaluate things like the flowability index. So you can see here that approximately the flowability index at a major consolidation stress of 10 is approximately about 0.7. So that is 7 kPa for the unconfined yield strength divided by 10 kPa for the major consolidation stress. So that product is displays high cohesive characteristics. And then another important aspect is actually assessing the particle to geometry interaction. So this is where we assess the sensitivity of wall friction with moisture content. So we're examining things like the wall friction on ceramic tile, arco plate, and matrox, which is a plastic liner. So you can see there that, actually the worst case moisture content is around about 13 to 14%. So it's slightly a little bit different compared to the internal strength testing that was conducted before. So you can see there at the lower moisture content, actually this material starts to become quite tacky. And this is where you expect to start seeing some build-up issues within your transfer chute. Okay, so this is obviously to be very mindful when handling product around that moisture content. Okay, so this will essentially govern what sort of what are the critical chute angles required to ensure that material will flow reliably. So you can see here from the wall frictions at low pressure are approaching near 60 degrees. So essentially we need to ensure that our chute slopes are greater than 60 degrees. Okay, so usually we add a buffer of about 10 to 15% on top of that, ideally. But you can also see here that ceramic tile typically displays the highest wall friction compared to arco plate and matrox. So if we're looking for a product to minimize buildup, we may select a product like arco plate, which can handle some wear and tear as well. So then we also conducted the rock box testing at 2 different moistures. So this is like a moderate nominal moisture content where we examine the drained angle of repose and the dynamic angle of repose in the bottom. And then we also conducted the same testing with a higher moisture content product. So this is closer to that worst case condition. So you can see there is a difference in that material flow behavior. This one is definitely a lot more cohesive, where you've got like clumping and agglomeration of material due to impact down the bottom here. And you can even see within our calibrated EDEM model, we've got some of those characteristics sort of shown there with that clumping of product and also the higher drained angle of repose. So once we've developed our material model and we've got our CAD models, we can actually start to run some EDEM simulation. So here just shows a simulation conducted of the as-built design using the moderate cohesive product. And you can see here what we can do now is actually verify the performance from our DEM in terms of the general material flow behavior, build-up characteristics, and compare them to videos and photos taken from site. So you can see there that we actually have that material building up in that micro-ledged chute where you've got that secondary flow and roping occurring. We've got a spray of product as it free falls into that lower chute. So we've got a very uncontained profile of product falling into that lower chute. We've got a high volume of material building up in this lower chute as well. So over time, that can potentially, if you're having dealing with more sticky material, can choke that chute. So the good thing with this sort of V-plate arrangement, you can see there that material does centralize quite well onto that outgoing conveyor, but material is directly dropping onto that receiving belt. So there's not very much momentum or velocity in the direction of feed. So here just shows the same simulation, but this is actually using the higher cohesive model. So you can see that there is a little bit of a change in the general flow behaviors with more clumping and sort of shedding of material as material flows from that head chute into that lower chute. We've got a greater volume of material building up in that head chute. You can see here, the material when it actually flows into this lower chute is slightly a little bit off center. So this, especially with this higher cohesive material, over time, there's a higher propensity that this product will just continue to keep, building up. And you can see there that, there isn't much clearance, say, for example, from the top of the material to that corner of that chute. So if you get a surge of material coming through, there is a risk that this may block. Okay, so then what we wanted to do was we identified some key problems with this chute. We have some issues with how that material is contained and managed in that head chute feeding into that lower chute, and then we have that rock box, which isn't ideal to keep, because material keeps building up. So what we wanted to do was look at installing our deflector plate into this head chute, as well as replacing this lower chute as well. So what we can do here is, what we did was basically below this blue chute is look at various design options. These included a smooth spoon and a ledge spoon. And we also looked at multiple other different design alternatives as well to see if we, for example, could look at doing some infill work on that lower chute to basically utilize that rock box type chute there. But basically we found that that was it was a much easier and viable option just to replace that whole entire lower chute. So what we did here is basically used our traditional analytical methods to design this lower chute in terms of optimizing this angle of this incline chute, and then more importantly that the radius and the cutoff angle on this spoon to try to match the discharge velocity to that belt velocity. And we also looked at using a ledge type spoon as well. So this essentially was looked at to see if we could try to minimize wear and tear around that high impact region on the upper section of that spoon. So here just shows a DEM simulation that was conducted with that ledge type chute. So this is just using the moderately cohesive bauxite material model. So you can see there that with this deflector plate, it does quite well to basically intercept that material as it comes off their head pulley, contain it, and then redirect it with a little bit of convergence into that lower chute. So I suppose one of the main benefits of having this deflector plate at the top there is to minimize that buildup, but also to have a little bit of control in redirecting that material into that lower chute. So you can see there around the impact point with that micro ledge chute, we have a little bit of buildup. So this could be potentially, problematic over time where that buildup may continue to increase. But once that material impacts that ledge, then it flows down nicely into this curved part of that chute where it is slightly accelerating and starts to deaccelerate around the curve, and then basically loads smoothly and softly onto that receiving conveyor there. So this is the scenario with actually using the smooth spoon in the lower section of that chute. So the characteristics and performance in the head chute are identical to the previous example, but you can see here down the bottom now is that, we have a lot less material building up around that impact point. Material tends to be flowing away from that impact point quite well. You can see there, you do have a bit of material that is pushing up onto the the sidewalls of that chute, but we have nice controlled velocity of that material in that lower chute. Okay, so one of the important aspects here is that we will expect to see some higher wear on its impact point, but the chute is doing quite well to manage the velocity and profile that product and the presentation, more importantly, onto that receiving belt, where there's very little boiling and build-up occurring on that belt in that load zone. So what I'd like to do now is actually show you a demonstration of the EDEM software and show you how we actually run a DEM simulation. So here shows you the EDEM software. Okay, so this is the preprocessor. And what you can see here on the left-hand side is our creator tree. And essentially what we want to do is essentially work our way through this tree. So you can see there that we have various items that we need to set up and define, like our bulk material, our equipment material. This is where we can import our geometry and set up our particle factories. Then we also have our physics here to look at our contact models. And then we also have some environmental settings as well in terms of defining gravity and the size of that simulation domain. So what I'm going to do now is just actually import a previously calibrated model. So what we've done is we've calibrated a model and we've stored that in our library, which we can use in any of our DEM simulation decks. So what I'm doing now is actually importing that material model into our deck. And you can see there that we have our bauxite material model. And this contains all the, the mechanical and interaction properties, as well as our contact properties as well. So you can see things like the solids density, which has been defined. So this basically governs what our bulk density will be, our stiffness of our particles. And then we also have here is our interaction parameters like coefficient restitution, static friction, rolling friction. And these things need to be calibrated but once we have these set up, then we can obviously use those parameters all the time. Then here's what we've done with this material model is use a combination of 3-sphere and single-sphere particles. You can see here what we tend to find is that we don't need to have extremely high fidelity particles to obtain sufficient interlocking and bulk material flow. So what we've done here is set up our shape. We can set up our particle size distribution if we like as well. So we can set up things like, I've set it up as a normal distribution, but if we like, we can also set up a user-defined based on a specified particle size distribution. Then down here, we have our equipment materials. So I've defined things like our ceramic tile. I've also set up a rubber equipment for modeling the conveyor belts. We have our steel for our chute work. And then also I've set up here another rubber model for the head pulley. So we have a little bit of control over how the particles are adhering to that head pulley, interacting with that primary scraper. So what we do now is we'll just set up our, we'll save our model. Okay, so I'll save this, just call it input. Okay, and then now what we can do is actually import our CAD. Okay, so within EDEM, we can import a wide range of standard CAD geometry. We can also import CAD directly from our 3D modeling packages, such as SolidWorks, Rhino, ProE, Inventor. But most of the time, a lot of CAD packages are capable to export models like STEL files, STEP files. So once we've exported those models, then we just import them into EDEM. So here, what I'm going to show you is the process to import them. These are all set up with meters. I'm going to merge this geometry. I'm going to rename the items using the file name. And the good thing within EDEM, what we can actually do here is if we want to control the meshing of our components, we can do that directly within EDEM by using this manual mesh size. And this allows us to, define the size of our triangular elements. So this is quite important if we want to, refine the curvature of critical components, but also for wear modeling when we want to have, a nice consistent mesh for modeling wear. So once I've selected that, I'll import this geometry. So it just takes a few seconds just to go through the routine to import the CAD. And you can see there now we've imported that geometry. So now what I'll do is I'll just save that geometry. And now what we need to do is work our way through defining what equipment materials to be used on each of our components. So you can see here, now we've got all our CAD items that have been pulled in. So these are just in separate parts. So you can see there we have our deflector plate. I've also imported the trajectory. So you don't need that, but that's just to compare, for example, the trajectory from the continuum-based models to the results we'll get from EDEM. So what we can actually do with these geometries is we need to define the material. Okay, so for that little deflector plate there we have, so that's just to prevent material from flowing into that primary sampler chute. Then for our trajectory, what we can actually do is make this a virtual item. So basically particles will pass through that geometry, and it's just used there as a background layer. Then we have our magnet, and what we can do for that is we'll specify that as steel, and we just we do that for all our parts. Okay. The next thing we also need to do is define. Let's set up the conveyor motion. Okay, so within EDEM, what we do is we actually don't model the particle physically moving, but we set up this virtual conveyor motion model. So by any particles that come in contact with that conveyor belt will move at a specified velocity in a specified vector. So I've set up that model. Now I actually want to set up a motion. So I go to add motion, I go to conveyor translation, and what that does is you can see here we set up that velocity. So we'll say this conveyor has a speed of 3.52 meters per second, and then we need to specify the direction. So what we do is actually we can use our geometry to pick points on our geometry to specify that vector. So you can see there that vector is defined by that blue arrow. So that is complete. Okay, and we do that process for all our conveyors. The next thing I'll set up is, say, for example, this head pulley. I'll say that this is a rubber conveyor. I mean, that's our head pulley material. And then we need to define rotation of this head pulley. So we assign motion, which is linear rotation. Okay, the speed of this is 80.6 RPM, and we also do the same here for the direction. So typically, when I set up my CAD models, I usually put the origin of the model in the center of that head pulley to make it easier to work with. So here the vector, I just put the direction in there. So you can see there you can see that blue arrow, which shows the way that head pulley will rotate. Okay, so that's now done. As I said, I'm not going to go through every step here with all the conveyors and assigning materials, but the next important thing to do is actually set up the particle factory. Okay, so within EDEM, we can define like a polygon for this generation of our particles. So that's where basically we initiate the particles into our simulation domain. But I've actually set up this in our CAD package, and then I'll use that for defining my factory. So you can see here I have the factory plane set up there. And then I've also put just a little set of skirts around that factory to contain that product so it doesn't fall off the belt. So what we want to do is set that up as a virtual item, and then we want to add a factory. So this would be a dynamic factory. We want unlimited number of particles. We want to set our flow rate. So we set it at 3,400 tons per hour. And then what we can also do is define an initial velocity. So typically you sort of set that around the belt speed. So that way that particles will come out of that factory at a high speed to ensure that there's space for new particles to be generated. So the good thing with EDEM is that it's quite efficient and has good performance with the particle factories. Okay, so essentially that's been set up. I'll also show you here, sorry, I forgot to mention this before, with the contact model. So here I've actually used the Hertz-Midland with JKR model. And typically what we need to do is define the surface energy. So that's basically the cohesive behavior of the moisture content indirectly between our particles. And then we can also do the same here for our geometry. So you can see we've defined various surface energy values between our particles and our geometry items or equipment materials. We've also set up the Chute and wear model. So essentially what this will do is we'll work between our particles and our ceramic tile product. So any product, or sorry, any part that has been assigned this ceramic tile equipment material will analyze wear as well. So we just need to define a couple of the parameters there for both the Chute and the Oppa wear model. The other thing we can do as well is just double check the gravity direction. So I always set up my models with gravity in the -z direction, which is the default for EDEM. And we can also change here our domain as well if we like, if we want to sort of reduce that overall simulation domain. So now that's been set up. And what we do now is actually move to our solver. So what we can do is we can use this auto time step, which essentially just sets a time step based at 20% Rayleigh. Then we set the simulation time. So I'll say 30 seconds I want to run this simulation for. I want to run this simulation at, save data at 0.05 seconds. We can also compress our created data files. So this basically would just reduce the overall size of the simulations on your hard drive. We can also use selective save. So this allows us to just pick and choose what information that we want to save during our simulation. So DEM produces or has a lot of information and attributes which is saved through our simulation. So what we want to do is typically we don't need to save all this information. So we may just go, look, we only care about the basic particle data and the velocity. We don't care about the angular velocity, the forces between our particles, or any of the other properties here like custom properties. We'll save all our geometry data. So if we want to have a look at the impact forces on our chutes and our conveyor belts, we can do that. And the interaction parameters, which has some contact and collision data, we don't necessarily want to save that for these type of simulations. Then down the bottom here, we set up our solver. So I want to use a CUDA solver. Then we just need to define things like our precision mode. So as I said, most of the time we'll use hybrid. And then typically we just have some additional settings down here that we can select as well to optimize our simulation and speed it up. So now that's been set up, we can actually run our simulation. Okay, so what I'm going to do is just run this simulation just for a short period, just to show you what you can do. So it just takes a little bit of time just to initialize this simulation, and then it will start to run. And the good thing with EDEM is that you can actually watch the simulation on the fly as well. So this is good to, identify any potential problems with the setup of your chute. So if you, for example, find that you've set up the conveyor direction the wrong way, you can stop your simulation and change it. So here's what I mean. You can actually see there that your particles are being updated on the fly, okay? So if you do see any problems, you can stop your simulation, go back, either rewind your simulation or just make the changes from that time step and restart your simulation. Okay, so once you run your simulation, so this simulation typically takes around about 3 to 4 hours to solve with the material model that I've set up using a GPU solver. So once our simulation has ran, what we can actually do is go into the post-processing. So you can see here, just shows you the setup of the analysts within EDEM. And what we can do here is also change things like coloring our particles, based on material velocity. We can also color our geometry as well. And we can clip our geometry. So you can see here we have some clipping planes set up to basically just neaten up our simulation here to remove, areas outside the region of interest. The other good thing that we can play back our simulations here, but more importantly, what we want to do is to make some assessments and further analysis of the performance of our chute and analyze that material flow behavior. And within our EDEM, we have what we call selection tools. Okay, so these are essentially different bins. So you can see here on the screen, we have some bins. For example, looking at the velocity of the material along the back of the chute. We also have a bin here, the discharge of our chute, which is an imported CAD model that we can basically, customize to fit around our geometry. Down on the left-hand side here, we have a series of mass sensors that can analyze the material distribution along that belt. So the type of sensors we can import things like manual selection, so we can select critical geometry items or particles. We have gridded bins, geometry bins, and imported bin groups. And then we also have some inbuilt sensors like mass flow sensors, velocity sensors, total mass sensors, segregation, solids, and bulk density. And then with these geometry bins too, the good thing is that within EDEM, you can actually manually move them around by just picking them and dragging them around on your screen. So we can also create videos and animations from these simulations, but we can also export data as well. So once we've set up our selection bins, we can export various queries from different time steps and look at things like, the exit velocity, mass flow rates, the forces on the conveyor belt. So I'll show that shortly, that, the various types of analysis that we can do. So if we go back, a bit of an overview of the various types of analysis. So you can see here, this is actually just showing the mass flow of material in and out of this transfer chute using the mass flow sensors. So you can see here, we've actually modeled a surge. So if we set up the factories to model, a 20% or 30% surge for a certain duration, we can analyze how that chute will perform under surge conditions. Even if you wanted to, you can model restart and shutdown scenarios. We can also assess the mass of material in the upper and lower part of the chute. So you can see here, I've exported and graphed the mass of that material for the various scenarios. So that's for the as-built and those two different design options. I also looked at the effect of, the as-built design with the high cohesion model. So you can see there with the higher cohesive model, there is more material building up in that lower chute. So it is the volume is quite sensitive to that moisture content and cohesiveness of that material. We can also look at the discharge velocity. So when we want to look at the velocity of the product leaving the chute and loading onto the conveyor belt. So here it just shows the two different sensors for the as-built and for the the spoon type arrangement redesign. And we can analyze things like the tangential velocity. So that's the velocity in the direction of the belt, the impact velocity. So that's the vertical component, and the lateral velocity. So you can see there that, we've got the belt speed at 4.2 meters per second. So the as-built design typically just drops that product vertically on the belt with a very low velocity in the direction of feed. So with this spoon design, you can see there that we're able to actually increase that velocity to get a better match between the discharge velocity and that belt speed. And you can see there, even with the impact velocity, by having that spoon there, we are actually softly loading that belt. And we also have a little bit of lateral velocity with this new design, but that's just mainly due to that location of that deflector plate. So we can adjust that positioning. So you can see here, what we can actually do within EDEM is, for example, is move that deflector plate and rotate it around and analyze that performance and the presentation of that product on the outgoing belt. So to analyze how that material is loading, we can look at the profile by using these mass sensors and doing some calculations of the center of gravity. So ideally, you want your material to be on the middle of the belt. So you can see there that with the current design with a V-plate, it's quite good to centralize that material. But you can see even with the redesign, we have a little bit of off-center loading, about 15 mil, which isn't significant to probably cause a lot of belt drift, but we can adjust it to reduce that down to around about 5 millimeters of belt drift. We can also look at that acceleration of material in the belt. So ideally, we want to accelerate that product over a short distance to reduce belt wear, stabilize and settle that material in the belt so that we don't have as much spillage. And you can see on the graph on the right here actually shows you the evaluated acceleration length. If we have a look at, for example, using a continuum model, we evaluate the acceleration length is about 430 millimeters. So when you compare that to the velocity profile from the DEM, you can see there that the actual redesigns with this spoon match quite well. Okay, so with the redesign, the material accelerates over a shorter distance, which is ideal to reduce belt wear. We can also assess the impact velocity on the belt. The impact forces on the belt by analyzing the contact forces in a region of interest. So here shows that geometry bin, which is used to analyze the particle to geometry forces in that box shown by the red outline. And what we've done here is actually assess the forces in the X, Y, and Z component. So you can see there that the forces in the X component have been reduced because of that shorter acceleration, which will be ideal to reduce belt cover wear. Within the lateral component there, we have a small amount of lateral force with the redesign spoons, but that's just because of that positioning of that deflector plate. But the most important thing here is like looking at the impact loads on the belt. So you can see there that there isn't a significant increase in the impact loads. So basically, because a lot of that load there is actually just the self weight of that material, which is good. So basically, it's showing here that the redesign should not increase the loads on the conveyor idlers that will potentially damage those idlers over time. We can also assess the velocity of that product along that spoon. So here just shows a plot of that velocity over the vertical distance, and you can see there that we got high impact velocities, and then the material is slowly deaccelerating to match that belt speed. So you can see there that we do have a relatively good match or close match between the belt speed and the discharge velocity. So what we want to look at here, for example, is making sure that that material doesn't deaccelerate too much, because if it starts deaccelerating too much, the depth of that material in that chute starts to increase, and we could potentially store and block that chute. The other thing we can do is look at the wear. So what we've done here is assess the impact and the abrasive wear on that lower spoon and on the deflector plate there. So on the right-hand side actually shows you the chute that was installed after many months in operation there. And it's hard to see there, but there is an outline that shows you the wear pattern on that lower spoon around that primary impact point. And that correlates quite well to the smooth line spoons there around that impact point. So you can see there's a good correlation between the DEM predictions and the real life. With the ledge design, you can see there around the wear bars on the tips of those ledges. We will expect to see high amount of wear, but also even what can occur is because of those ledges, when that material impacts again that smooth line chute, you can see that in that lower part of that spoon, we may see some hot spot of wear as well. But on the deflector plate, there's a lot less sort of wear compared to that lower spoon, so we can get away with using thinner liners on that deflector plate because it's not as subject to as intense wear. We've also conducted a two-way OptiStrut simulation to assess the stresses and the displacement on that on the as-built design as well, just to show you the capabilities of this two-way coupling. The other thing we've done is also looked at the stresses and the structural integrity of that deflector plate. So what we've done is using SimSolid, we've exported the loads between our particles and our deflector plate in a CSV file. Then we've imported those loads into SimSolid, and we've set up some boundary constraints around the shaft supports. And then we've run our simulation. So we imported our 3D CAD model. We can add things like worlds if we like, define our material properties, and then we can run this simulation. So the great thing with SimSolid here, it's very quick. So it provides that sort of rapid design exploration evaluation. So you can see these simulations are taking around about 40 seconds to solve. But you can see there with this deflector plate, the stress levels are quite low. So we don't necessarily need to put all the harsh or a lot of stiffening on this deflector plate. The other thing we can do is we've had a look at, for example, the scenario where if we have a crash e-stop where we crash the belt quickly, then you have material building up in that transfer chute. It acts as a storage vessel, and then we restart that conveyor up and pulls product out. So from that, you can see there we can have a look at how well the chute is performing to store that material, and then also how well it is performing to drain that product out when we restart. But we can also look at the loads. Okay, so we want to ensure that during an e-stop event and a restart mode that those pull-out forces won't damage the chute. So we can analyze the vertical loads in that chute during the shutdown process, and then during the restart we can analyze the tangential or the pull-out loads on that chute. And then we've run a SimSolid simulation again with that. This is with the micro ledge type design chute, and under the steady state flow conditions, but also the pull-out case as well. So under the steady state flow conditions, the stress levels are quite low, low deformation, but there is a little bit of a concern when we're pulling out that there are some regions here with higher stress that we may need to look at stiffening up those regions of that chute work. And again, the simulations are very quick to run, so they only took 32 seconds to run that structural analysis simulation. So here actually shows photos of the final chute design that was fabricated and installed, where we have that deflector plate and the lower chute here. So with the wear modeling, what we were able to do as well was look at, the thickness of tiles that are required in this lower chute to look at, we could see that on the back part of the chute, we needed thicker liners because it is experiencing higher wear. So we could put thicker liners on the back and then thinner liners on the side walls. So if we actually look at the chute in operation here, you can see there it works quite well in terms of regulating the material velocity, containing that product, and minimizing any sort of buildup in that lower chute. So we have nice, soft and controlled loading onto the outgoing conveyor. And there's very sort of minimal buildup occurring within this chute. So this chute has been operating for many, many years now, with no reported blockages, but they do need to regularly replace the wear liners within the chute. So they ended up deciding to go with this smooth line chute over the micro ledge chute, just because there was a higher risk that there would be build up around that micro ledge impact region. So they wanted to basically minimize that risk and went with using these smooth liners just to ensure that the chute would operate reliably. And you can see here with the utilization of DEM simulation that we're able to have high confidence that the chute would perform in accordance to the results from our simulations, and provided the key stakeholders confidence that it would be a reliable chute modification. So that allowed them, to basically gain the confidence to conduct the engineering and fabrication and the install of the new lower parts of the chute and that deflector. So just to summarize what we've covered in this webinar. So the DEM capabilities and simulation tools within Altair allow designers to conduct more complicated and advanced scenarios using co-simulation, and it provides realistic simulation and insights into the equipment performance, and allows designers to conduct a lot of what-if scenarios, examine a lot of real-life scenarios in a virtual environment in a quick time instead of doing scale modeling or trial and error on site. And it also provides increased confidence that the solution will work, reduces the sort of risks and costs with failed solution, reduces the amount of prototyping required, reduces any sort of production risks as well, especially when restarting operations if a chute doesn't perform as intended. And overall, it improves the operational efficiency. So thank you very much for attending this webinar. I hope you found it enjoyable, and I've provided a lot of good insights in the utilization capabilities of the Altair simulation design tools. So this is an opportunity now to ask any questions if you have any. Thank you very much.
First of all, we want to give our thanks to Andrew for that very insightful webinar. A lot of valuable information has been shared. As mentioned in the chat, we will share a recording of it as well. Thank you, everybody. With that, we'll then end the webinar. Thank you, Cynthia and Prasad, for your time as well. Have a great day.